Hello students. In this lecture we will be talking about electrical conduction in thin films. Thin films are a major constituent when we are dealing with uh, nanoelectronics, because a thin film is a two-dimensional nanomaterial. So the transport properties or the electron conduction properties is a very ingredient part of nanoelectronics when we are dealing with electrical conduction in thin films. Now, first we will consider that the electrons are not bound by any potential. That means the free electrons. If the electrons are free, then the electrical conductivity in a metal, let's say we are talking about a metal, so electrical conductivity will be according to the Drude Lorentz Sommerfeld theory. The Drude Lorentz and Sommerfeld theory, which according to them the conductivity sigma is equal to n E squared L by mv, where E is electronic charge, L is the mean free path, m is the effective mass or the mass of the electron, and v is the velocity of the electron, and n is the number of electrons per unit volume. There are basically two types of internal energy that are present while discussing the Drude model. The first one is the free energy. And we can also call it the kinetic energy of the free electrons. And the thermal properties of solids depend totally upon the change in the energy of lattice and free electrons. Solids, they depend upon change in energy of lattice and free electrons. Now, when we are applying an electric field, naturally the free electrons will be accelerated So electric field, when applied, they will accelerate the free electrons, and which will lead to increase in their kinetic energy. And a part of the energy is lost with lattice, and so there will be collisions that will lead to collisions, increase in kinetic energy, and what will happen that a part of the kinetic energy will be lost with the lattice atoms. This will result in a change in the current density proportional to the velocity of the electrons. So this will lead to a change in current density proportional to the velocity of the electrons. So in between these collisions, suppose there is a collision that has taken place. So this is the collision. They follow a zigzag path. Now in between collisions, the electrons move with uniform velocity, but during every collision, both direction and magnitude of the velocity gets changed. So direction and magnitude of velocity changed after every collision. So this is actually the second type of energy that we talk about. So call it B. There is one, the internal energy, and second, the energy with the collision. Now, electrical conductivity in a metal is directly proportional to L. L is the mean free path. So, and after every collision, the time between two collisions is, of course, called the relaxation time. And resolution time is T is equal to L by the velocity of the electron. So if we divide conductivity by L, we will get 1 by rho L, which is equal to n square n by mv, and it is again equal to 8 pi by 3 to the power 1/3 into e square n to the power 2/3 divided by h, and this is actually equal to 7.1 into 10 to the power 7 n to the power 2/3. Now you may question where this, from where do we are actually getting this quantity. So this is actually the volume, or the volume density. You know that if we consider the electron, or the consider to be electron to be moving in a sphere, so the volume of the sphere is is equal to 4/3 pi r cube. Now, considering that the electron after collision it moves in two different directions. So if the electron is flowing, suppose in this direction, it collides with the lattice, and again it moves in the opposite direction or any direction which is not exactly this direction. So therefore, during these two parallel motions, what we do, we associate an extra quantity 2 with it. So it's 2 into 4, that makes it 8 into pi r cube. This is actually the volume. So when we are considering the number of electrons per unit volume, this n, this is actually getting multiplied by this 1/3 of this value, or this v is the velocity. So that's how we are getting 8 pi by 3, and other quantities are remaining the same, or the mass of the electron. And also we can say that sigma by L is equal to E square by 6 pi square into A by H. This is considering the area, where A is equal to 4 pi into 3 pi square n to the power 2/3. So surface area is 4 pi r square. So instead of using r square, we are using this value. So this replaces the r square. R is basically 3 pi square n to the power 1/3. This is the r. So that's how we are getting the r. 4 pi r square is square of that. And this whole sphere that we talked about, this sphere is actually, or the surface of the sphere is actually the Fermi surface, this A. So we can see that the ratio sigma by L, this ratio, it determines directly the number of conduction electrons per unit volume. Determines the number of conduction electrons per unit volume, and the area of the Fermi surface, and area of the Fermi surface. Now, when we talk about the distribution function of the conduction electrons, so let's talk about distribution. Of conduction electrons, how they are distributed. So we need to consider the Boltzmann equation. And this Boltzmann equation is found by equating the rate of change of the Fermi-Dirac statistics to the external fields. It is by equating the rate of change F stands for here is the Fermi-Dirac. Fermi. I hope you know what is the Fermi-Dirac equation. Those from electronics might be knowing it. Those from electrical engineering might be knowing it. Anyway, you must have studied in your basic physics course. So, equating the rate of change of F, that is Fermi-Dirac function, and it equates this to the external fields, and this change is due to external fields. To the rate of change due to collision mechanism. So it is the rate of change of F due to external fields to the rate of change of collision mechanism. Now, in the presence of electric field E, when we have electric field and magnetic field H, the Olson equation takes the form minus E by M E plus V cross H into gradient of F plus V dot gradient with respect to R F equal to the rate of change of F due to the collision. This is the equation. And this equation is basically the analysis of size effect and it involves space derivatives. So this is the space derivative of F, R, which takes into account the non-uniform distribution in space of the conduction electron. So since F is distributed and since the conduction electrons are non-uniformly distributed in space, so this gradient, that's how this gradient terms come into this equation. Now this equation, now if we coming to an equilibrium value, if we say that the rate of change of F is now in equilibrium with the rate of change of F due to collisions, so we can write F minus F1 T is equal to F minus F0 T is equal to 0 into the power minus T by tau. That means at a certain time, relaxation, considering relaxation time, you can have this equation where L is equal to V into tau, that we have already discussed, and a free path can be defined by scaling by randomly distributed impurity atoms as well as the lattice vibrations if the temperature is above the Debye temperature. So if the temperature is above the Debye temperature of the lattice, then we can actually define a free path of the electron by impurity atoms as well as for the lattice vibrations. So the impurity atoms and lattice vibrations are to be also considered while considering the free path of the electrons. Impurity atoms and lattice vibrations.